In this video, this short video, I just want to show you, give an example of how Reynolds number can affect lift and why in some cases we can ignore that. And this comes in the context of scaling and model scaling. What happens if you put a model in the tunnel, a wind tunnel, and you can measure the force, say the lift force on that model, but the Reynolds number is not the same as the full scale. Is that lift force, under what conditions is that lift force relevant to the full scale? So what we use is a code called XFoil, which can predict the lift and drag. We'll focus on lift here, generated by 2D sections. And I'll show you how the effects of Reynolds number modify the pressure distribution and the resulting coefficient of lift. So I'll just give an example of that. So if we start XFoil, I'll focus on, say, a symmetric foil, a 0012, and I'll first run it in, say, a Mach number around 1,000,000. So I'm going to run this as a viscous case with a Reynolds number around 1,000,000, and an angle of attack of 2 degrees. And this should produce the plot. I think what I'm going to do is shrink this a bit. So let me redo this. Okay, so it produces this plot. And we'll be seeing these a lot during class, but I'll just give you a synopsis of what we're seeing here. This is the pressure distribution on the upper surface, the blue, and the lower surface, the red, of the wing. It's shown not here at an angle of attack, but it is at an angle of attack of 2 degrees. This is the suction side of the aircraft, so the air is moving up towards it like this. This is where the low pressure is. We're plotting here pressure coefficient, and we're plotting the inverse of pressure coefficient. So the y-axis is flipped upside down, so this is positive in this direction. That means lower pressures are higher on this axis, and higher pressures are lower on this axis. The stagnation point's here. Stagnation point has a pressure coefficient of exactly 1. We'll discuss that in a few weeks. And as we travel, the flow travels up and over the upper surface. It is accelerating here to lower pressures, again, more negative pressures. And then after it goes through what's called the suction peak, it starts to decelerate until it reaches the aft end of the vehicle, of the wing. The lower surface also starts a stagnation point, so the streamline will split here, and the streamline will go below the foil, and that's what's seen here, this pressure distribution. It also goes to negative values, indicating it's faster than free stream, but doesn't reach the same negative values here. And it's really the difference between these two pressures at any given station that's that's responsible for the lift force on the foil. And this will close out at the end. Also shown here is what's called the inviscid lift distribution, which is the dashed black line. That's the pressure distribution you would see in the absence of viscosity, in the absence of boundary layers. And so XFoil doesn't explicitly create boundary layers. It uses an empirical method, which includes also the displacement thickness, the effects of the boundary layer pushing this pressure, modifying the pressure distribution somewhat. The air essentially sees a slightly thicker foil. And you can see that here. It may not be too easy to see in the video, but that the blue line, which represents the outer part of the boundary layer, is displaced from the foil surface. So there's some thickness. There's thickness everywhere in the boundary layer. It's most apparent at the aft end of the foil where that thickness is. And that has some effect on the pressure distribution. You can see the suction peak is somewhat reduced, in particular for the case with a boundary layer versus the inviscid case being essentially imaginary. You also see this bump occurring here. This is due to transition of the boundary layer, which we'll talk about in our viscous lecture, occurring about halfway back on the foil, somewhere around this station right here. So let me leave that pressure distribution up for a second, and what I'll do is open another terminal, and I'll start XFoil again. And let's just run a different Reynolds number. I think I ran a million on that. So if I'm going to use the same foil, a 0012, I will set the Reynolds number to be, say, 5 million, And I will run this at the same angle of attack, and I'm going to do what I did last time and resize and replot. Plot it over here. Okay, so everything's the same here except the Reynolds number is significantly higher by a factor of 5. You can see that the pressure distribution, the inviscid pressure distributions in these two cases are identical because that has nothing to do with the Reynolds number. It's simply a matter of the foil, which is the same, and the angle of attack, which is the same. The pressure distributions in the presence of the boundary layer, which is given by the blue line for the upper surface and red for the lower surfaces, you can see they're very similar. Maybe the most notable difference is the location of this bump has moved forward. That's the transition of turbulence has moved forward on the foil at the higher Reynolds number. But the deviation from the suction peak and the general shape is very close to the inviscid distribution on these foils. So these are a factor of 5 different in Reynolds number. I can do one more. Let's try dropping it down. X-foil's not going to like it if I go too far down. But let's try perhaps 500,000 and see if we can get that to converge. So let's do 500,000 and angle of attack 2, and I'll do the same thing. Here. Okay, so we're seeing 1 million in the upper left, 2 million in the upper right, 500,000 in the center bottom here. But again, I truncated our pressure distribution. Let's open this up a bit. Try again. And you can see that as we go from the highest Reynolds number, at the highest Reynolds number, the flow field with the Reynolds, with the boundary layer place, is very close to the inviscid solution. And as Reynolds number goes to infinity, we should recover the inviscid solution. As we drop the Reynolds number from 5 million to 1 million, you can see there's some deviation at the suction peak between the two curves, the inviscid and the pressure distribution with viscosity. And you see it getting even further apart down here as we drop the Reynolds number down to 500,000. That the deviation from the inviscid curve is greater, and that's because the viscous effects are becoming more important. Also, transitions move further back. So if we go from here to here to here, we're increasing the Reynolds number, and the transition point is moving forward. The boundary layers are becoming thinner, and the viscous effects, although there is still a strong drag effect, the effect on lift relative to the inviscid case is being reduced as we increase the Reynolds number. I don't know that X-foil will tolerate anything less than this. We might as well give it a try. So I'll do upper, I'll do visc, try 250,000 and alpha 2, and I'll shrink this. Yeah, maybe having trouble converging. So I think I'm going to leave that out because I'm not trusting this solution so much. Let's stick with these three as a comparison. And one more thing I want to show you. So if we look at the lift coefficient that gets generated as an angle of attack on this particular foil, so fix the foil, we're going to range the angle of attack, look at the lift that is generated, and then we're going to see how that lift is affected by see where that is. Reynolds number. So this is angle of attack in degrees, alpha, and these curves will be seeing quite a few of these during the semester. And this is the lift coefficient. An angle attack of 0, we produce 0 lift because it's a symmetric foil. As we increase the angle of attack, the lift goes up. And you can see, with the exception of the very low Reynolds number curve, that lift slope, this is called the slope of the lift curve, the rate of change of lift with respect to the angle of attack is pretty linear. In the highest Reynolds number curve, which is 10 million is the black and 5 million is blue, they're almost coincident. You can't even tell the difference between them because they're sitting on top of each other. And they are essentially lines up until around here, and then you see they start to deviate from that linearity. And this is due to a thickening of the boundary layer and the onset of stall as we reach sort of a peak lift coefficient. But in this sort of range here, 0 to 10 or 0 to 8, you're talking about very linear, for the high Reynolds number, a very linear lift coefficient, and nearly linear at 1 million. The deviations occurring at this low Reynolds number curve. And what we're seeing here is a convergence in terms of Reynolds number. As we go from 1 to 5 million, at lower angles of attack, the lift coefficient is relatively insensitive to that Reynolds number. If we get to very small Reynolds number, then we start to see a sensitivity, and if we were to drop the Reynolds number any more, this would deviate further. But in this sort of range, and again, if you think back to the short video I put up talking about Reynolds numbers, we're thinking about millions for wings. Cessna's about 7 million, the glider was about 3 million, the 747 was about 50 million. That's an extreme upper end. So if you're thinking about sort of these vehicles, we're talking in millions up to about 10 million. So you're thinking about we're really in starting somewhere between green and blue up until above black. A little above black comprises much of the aircraft that we are thinking about, just in the nature of where they're flying and the general dimensions, how fast they're flying, and the general dimensions of aircraft that humans use. And so you're talking about this regime right here. If we were to consider insects, we were to consider the fruit fly, we're talking about a very different situation. And so we wouldn't be able to say that that the Reynolds number has only small effects on the lift. But in this case, we're talking in this regime right here, fairly in the linear sense. You can see that there's a deviation among them at high Reynolds number. But in this linear range, down here, lower angle of attack, for a given angle of attack, you are getting very similar lift coefficients. So when we think about, for our low Mach number flows, our lift coefficient being a function of, for a given foil, being a function of angle of attack and Reynolds number. Here we're seeing for low angles of attack, with attached flows, that even the Reynolds number isn't that important. It's really the angle of attack is by far the most important factor. So if in our tunnel we aren't able to achieve the same Reynolds number, but we are able to achieve the same angle of attack on a model scale, that we can see that the lift coefficients that are generated in this range are pretty good, provided, for example, if in the full scale it's 10 million up in the air, and in our tunnel it's 3 or 4 million, we can't get it to 10 million, but those curves are very close together, and there are actually also correction factors you can use as well. But this is a point I wanted to make. This doesn't, on the drag side, it's a different story, and so we have to start thinking about that and how we would correct for that. But on the lift side, because lift is connected to pressure, and pressure is not that sensitive to the boundary layers. Once they get thin enough, provided the flow stays attached, we have this situation.